just want to do a trigonometric substitution problem involving a definite integral since we haven't done one of those yet. The so the problem here is to evaluate the integral from 0 to 2 of the square root of 4 minus x squared. So what we want to do is we'll just start this the regular way. We can see that this is an a squared minus x squared type of substitution. So we'll just let x equal 2 sine theta. You can review why that's the correct substitution in previous videos. And dx equals 2 cosine theta d theta. So we're going to start this just the regular way. What we can do is we can observe that the square root of 4 minus x squared is equal to the square root of 4 minus 4 sine squared theta, which equals the square root of 4 times the square root of 1 minus sine squared theta, which is 2 square root of cosine squared theta, or 2 cosine theta. So we now have we have everything that we need to do the substitution. We can simply write that the original integral, I'll just put 3 dots here for that, is equal to the integral of 2 cosine theta then times 2 cosine theta d theta. So just to be clear, this is the square root of 4 minus x squared, and this is dx, so everything in the original integral is accounted for. The thing you have to remember here, though, is that this is, in fact, a substitution, and if you recall, we made a big deal with u substitution over the fact that when you change the variable, you have to change the limits of integration to match the variable. So it would be incorrect, for example, to just write 0 and 2 like that. So instead, what we can do is we observe that x equals 2 sine theta. So let's see, if 0 is equal to 2 sine theta, well, sine theta is 0 when theta is 0, so it actually is correct to write this 0, but we want to make sure that that's correct for everything. It's not going to be correct for the upper limit of integration. So let's see, 2 equals 2 sine theta. That means that 1, I'll write it over here, so 1 is equal to sine theta, which means that theta equals pi over 2. So the correct limits of integration are now 0 and pi over 2 instead of 0 and 2. So the nice thing about this is, since we've changed the variable, we don't need to do any back substitution. We don't even need to use the triangle for this. It's certainly true that if we're looking for just an indefinite integral or an antiderivative, we would need to put the answer back in the original variable. In fact, I hasten to add that I see every year answers to the trig subproblems where people leave the answer in theta and they think that's okay. It's not okay. It's just that here we're not even trying to get a variable answer, we're trying to get an actual numerical answer. So here we can just write the integral from 0 to pi over 2 of 4 cosine squared theta d theta. Now, we know from an earlier problem what the antiderivative of cosine squared is. So this is going to be 4 times 1/2 theta plus 1/2 sine theta cosine theta. We did that in an earlier problem, so I don't need to do it again. And that goes from 0 to pi over 2. Simplify this a bit, and that becomes 2 theta plus 2 sine theta cosine theta from 0 to pi over 2. And now we can just we can just substitute those numbers in. So we're going to get 2 times pi over 2 plus 2 times the sine of pi over 2 is 1. The cosine of pi over 2 is 0, and then we'll subtract from that 2 times 0 plus 2 times the sine of 0 is 0, and 2 times and the cosine of pi over 2 is 1. So fortunately, this is just 0, this is 0, and this is 0, and that leaves me with 2 times pi over 2, or just pi. Now, just notice something here. This expression, the expression square root of 4 minus x squared, that's actually just the top half of a circle or a semicircle like that, a semicircle of radius 2. So if I'm integrating from 0 up to 2, what I'm really doing is I'm just finding that area. So that makes complete sense, because a full circle of radius 2 would just have, a full circle of radius 2 would just have an area equal to pi times 2 squared, or 4 pi. So what I actually found here was, I'll just draw in the full circle, I found the area of a quarter of a circle, which is pi. So I told you that maybe we'd get a little bit of intuition about why these antiderivatives are what they are. Hopefully that at least gives you a very little bit of intuition about that. But the main point of this example is to show that if you're finding a definite integral, you don't even really need to do the back substitution. You actually just need to change the values of the values of the limits of integration into the new variable theta.